Hello, my DE super chemist out there in King William. I hope you're ready to dive into chapter 12 with me, which talks about crystalline solids. Now, a lot of this is going to be new because we didn't cover much of it last year for a couple of reasons. Last year was abbreviated, so some of the stuff had to be taken out, and this was one of the things we had to take out. All right? So, no worries. It's going to be super easy for you guys because you guys are super smart. So, I'd like to start talking about chapter 12 by talking about crystal lattice structures. And you see I've got my notes up for you too. Remember that the notes are posted in Schoology, so you can have the PowerPoint up and you can listen to my exciting video all at the same time. Okay, so there's three types of lattice structures we're going to talk about this year. Simple cubic, which is just a cube that has an atom on each corner, okay? There's face-centered cubic, which looks like simple cubic, except there is an atom on the face of each side of those cubes as well, and body-centered cubic. And I am not going to try to draw those. Your book has wonderful illustrations. There's good illustrations in your notes. There we go, okay? So we're going to start by talking about simple cubic first, and we are going to be doing some calculations with these, all right? So there's simple cubic. That's what it looks like, okay? Now, there's a couple of things we need to know. In a simple cubic structure, there is essentially one full atom. Well, why is there one full atom? Because when you look over here at this illustration, and there's one in the book just like it, there's about an eighth of an atom in each corner. And there are 8 corners, 4 at the top and 4 at the bottom. And 8 times 1/8 is 1. So we assume there's one full atom in that. There's some other interesting information that you should know. The edge, okay, so the edge of that cube is essentially 2r. R stands for the radius of that atom. And if you look at the packing efficiency in the simple cubic, about 52% of your space is occupied by an atom. That means that 48% of your space is just empty space, okay? So there are body-centered and face-centered that we can pack atoms with that gives us a little higher occupied atom space, okay? Less empty space. Now, the next type of crystal your book talks about is body-centered. Body-centered looks just like what we just looked at, the simple cubic, except right smack dab in the middle is another atom. So technically, if you looked at the cube of that atom, okay, right here, there are about 2 full atoms inside that cube if you were to cut a cube section out. The edge length is 4r, so that's 4 times the radius divided by the square root of 3. These are things you're going to have to remember and know. And the packing efficiency here is 68%, so I have less empty space, okay? The last type of cubic or lattice structure that chapter 12 talks about is face-centered. So I'm looking like that simple cubic structure, except all around the face I have another atom. And because of this, there are actually 4 full atoms inside the face. The edge length is now going to be 2 times the square root of 2 times r. R stands for radius. Too early in the morning to be taping these notes. Woohoo! And the packing efficiency here is 74%. So a lot less empty space, a better utilization of the area around us. Okay? I started the notes after we talked about the different lattice structures just by doing some examples. And I asked you to identify, what these structures were. Okay? And the polonium is obviously a simple structure. And because it's a simple structure, because it only has 1 atom in each corner, the total volume inside that cube is going to be 1 atom. And the tungsten is going to be body-centered. You have 1 on each corner and 1 in the center, so that's going to be 2 atoms. And the last one was face-centered, so that's going to be 4 atoms. Now, I like that example because it makes you visualize and classify the lattice structures. But what I really, really, really like are the next 4 examples, because they throw some numbers into the mix. And I'm a numbers person. I like numbers. So I'm looking at the first example in your notes. A body-centered unit cell has a volume of 4.3 times 10 to the negative 23 milliliters. Now, I know that a milliliter is just a cubic centimeter, so that doesn't give me the heebie-jeebies at all. Find the radius of the atom in picometers. Okay, so here goes. Let me see. I know that the volume of a cube is just the length cubed, okay? I know that from geometry class from a long time ago. And I know that means that volume or that length is just that. All I did was rearrange that, just like you would do, or that L, I should make those congruent. These are both lengths, okay? All I did was rearrange it like you did in algebra class back in middle school, okay? Easy peasy. Now, when I go to find length, it is 3 times 4.32 times 10 to the negative 23, okay? Because that's in milliliters, it means it's in cubic centimeters. So when I go to find my answer, that is the length of that cube, okay? Now, I know that from my notes that we just took, that's what length equals. And I know that because it is body-centered. I had to tell you what type of lattice structure it was, or you couldn't get that right, okay? So I know that length is 3.5 times 10 to the negative 8 cubic centimeters. Radius is what I'm looking for, divided by the square root of 3. When I put the square root of 3 in my calculator, I got that number, okay? So now you should be able to just put that over 1, cross multiply, and find that x is equal to that many centimeters. All right, so that's the radius. But, see, I was mean. I flew in on my broomstick, and you need to read these questions carefully because I specifically said at the end, find the radius of the atom in pm. So you have to convert that to picometers. So I'm going to put that over 1. That's not a big deal for you guys. We've been converting from picometers and centimeters and metric units for 2 years now. Easy peasy. 100 centimeters is 1 meter. 1 meter, 1 times 10 to the 12 picometers. When I say pico, you say 12. Pico, 12. Pico, 12. Okay? So, we know that that's super easy. I plug that in my calculator. Shazammy poo-poo. That's my answer. If you leave that answer in centimeters, will I take points off? Heck yeah. Okay? All right, let's do another example because these are so much fun. All right, so I'm looking at the next example in your notes. Okay, so I'm going to flippy poo-poo. Okay. Aluminum crystallizes with a face-centered cubic. See, I have to tell you the lattice structure. Unit cell. The radius of an aluminum atom is 143 picometers. Calculate the density of solid aluminum in grams per milliliter. Milliliter just means cubic centimeters. That's not going to give us the heebie-jeebies. So the first thing I like to do, okay, call me crazy poo, is I'm going to find out the mass, all right? So I know that I have 4 atoms of aluminum. How do I know I have 4 atoms? And I'm going to switch because this doesn't seem as dark. So I'm going to write in this color. Well, how do I know I have 4 atoms of aluminum? Because I told you that it was face-centered, and all face-centered has 4 atoms. So I'm going to find out what the mass of these 4 atoms are. Well, the first thing I'm going to do is convert to moles using Avogadro's number. And then I can convert to grams. Moles gets 1, grams gets the number from the periodic table. And so the mass of 4 atoms should look something like that. All right, well, I'm calculating density. Because I'm a super chemist, I know density is mass over volume. So I now have mass. I need to find volume. Well, from the last problem, remember, volume is just length cubed, right? So I'm going to have to find the length, right? So because it is face-centered, I know that the length uses that formula, right? And so now I want you to look at something that I did there, okay? When you're finding length, I converted length to meters just to make my life easier. Because when I did all of that, I ended up with 5.7 times 10 to the negative 10 meters. And I can quickly convert that to centimeters. 1 meter, 100 centimeters. Is this going off? Oh, this is going off. Hold on. Let me write it underneath then. This is going to equal 5.72 times 10 to the negative 8 centimeters. All right, I can do something with that because I know that density is mass over volume. And I know the mass is 1.8 times 10 to the negative 22 grams. I know that volume is length cubed. Well, I know that that's volume, 5.72 times 10 to the negative 8. And I'm going to cube it. And cubing that doesn't give me the heebie-jeebies because I'm just cubing centimeters. And when you cube centimeters, it's just milliliters. So when I plug all of that in my calculator, that's my final answer, okay? This is going to conclude part 1 of your Chapter 12 notes for Chem 112. I hope you join me back here for part 2. Toodles poodles, see you in class.